Welcome to video lecture E2. This is on solving systems of linear equations. So we know what a linear system looks like now. We'll call two linear systems or systems of linear equations. It means the same thing. We'll call them equivalent if they have the same solution set. Okay, so they could look very different, but if they have exactly the same set of solutions, then we call them equivalent. And we'll define something called row operations, which will be very natural, and they change linear systems into equivalent linear systems. By using successive row operations, we'll be able to change a linear system to a simpler one that will allow us to find the solution. And we can view the same process as working on corresponding matrices that represent the linear systems. The matrices basically forget about the variables involved and actually make it, even just from a bookkeeping standpoint, they're easier to use. But it turns out that that level of abstraction actually becomes much more powerful and is used throughout the course. All right, so let's just remind ourselves, we solved this system of equations last time, the last video lecture, I think. And so what's going on here is that we've got, one way to think about what's going on is that each of these represents two intersecting lines, right? So if I wanted to do something like this and draw a graph, what would I do? Well, I actually know the solution, as I recall, was 5, -2, right? So let's suppose that this is 5, and then this is -2, so this is the point 5, -2. And I know that both of these lines go through that point, right? So at the beginning, what I have are like two lines that are going through this point at some angles, okay? Now, what happened at that next step where I replaced my system with a different system is that, okay, my solution is still 5, -2, right? And that hasn't changed because when I multiplied one equation by 2 and subtracted it, or multiplied by -2 and added it to the other one, that didn't actually change the solution set. The solution set is the same, but now notice that this is one of the equations, right? This is the equation y = -2. And then the other equation is still slanted on an angle as it was before. Okay? And now finally, let's see, I guess I wrote the same one twice unnecessarily on the slides. But then in the third set of equations, I've still got 5 and -2 here. But now what I've got is that the equations are, okay, there's one equation y = -2, and there's one equation x = 5, right? And so now what I've done is I've replaced, so the solution point is the same in both cases, but I've taken the lines, and instead of having them be at some weird angle, I straightened one out, and then I straightened the other out to put them in simplest possible form. Okay? So that's, and it's a small example of what's going on, but that's the idea of what's going on. Since what I care about is not the equations themselves, but just the solutions, I do things to the equations that make them simpler and preserve the solution set. It's a powerful idea in mathematics to, try to figure out the thing you care about and then figure out what doesn't change the thing you care about. And, but you can make other changes around that. Okay, so what are the three elementary row operations? There are three that we need. One is that you can always add a multiple of one row to another row. That's the critical one. That's the one that allows you to eliminate variables, and it plays a major role in the class. Interchanging two rows, I mean, that's useful too. It's just a way of kind of making sure that the ones that are most easy to use for eliminating other rows go at the top, and to make sure that you have like the things that are mostly zeros, zero coefficients down at the bottom. And finally, multiplying one row by a non-zero constant is often useful, like dividing the 2x = 10 by 2 to get x = 5 in that last equation right there. Okay? So none of these operations changes the solution set of the system of linear equations. Okay? So that's the key idea. And we'll call two linear systems row equivalent if there's a sequence of row operations that takes one to the other. And the idea here is that row equivalent implies equivalent in the sense of having the same set of solutions. All right, so let me do one example for you full on. so that you can see how this technique works. So I want to be systematic. So I'm going to try to have only one equation with x variables, and then have only one equation, and then I'm trying to make things sort of triangular. So you'll see what happens. So I'm up here, and the first thing I want to do is interchange two rows. I want to make my top one be 2x space minus 6z equals -8. I want to make the next one be y plus 2z equals 3. And then the last one will still be 3x plus 6y minus 2z equals -4. Okay? So now I've got this system. And now for the next system, what am I going to do? Well, let me divide through this 2, right? I'm allowed to multiply by any non-zero number, so I'll multiply by 1/2, right? So I'll get x, leave some space, minus 3z equals -4, right? Then I'll have y plus 2z equals 3. I'm trying to do only one thing at a time so as not to confuse you. Later on, when you get bored with this, or you get skillful at it, which amounts to the same thing, we'll do multiple steps at a time. Okay? So far, what have I done? I interchanged two rows, and I rescaled one row. Okay? So now that I've rescaled it, it's easy for me to think, how can I eliminate? There's nothing to eliminate here already. This is a 0x coefficient. But if I multiply this equation by -3 and add it to this equation, then I'll get rid of that variable there, and that's really good. Right? So then I'll have x minus 3z equals -4. And I haven't changing this. I'm doing one thing at a time. Equals 3. And now multiply by -3 and add. That means there'll be a 0 coefficient there. All right. And now what happens? There's no y. The y coordinate's unchanged. But now here something happens, right? Multiply by -3 and add. I have -3 times -3 is plus 9z that gets added to 2z. And so I get a plus 7z. And now I put -3 times -4 is plus 12 added to -4. And I get plus 8. Okay? So when there are minus signs around, things can get a little bit tricky. And so that's why I prefer to always multiply by something and add, because when I think about subtracting negatives or something, I get it wrong half the time. Okay? So now one thing that's worth noticing is that you could actually have thought about all of this just in terms of the coefficients, because all we're doing is changing the coefficients. So one way to think about this is as a matrix, right, where this is the matrix 0, 1, 2. Then I'm going to put a vertical bar to clarify where the equal sign is. And here I'll have 0. Here I'll have 2, 0. Make sure that's clearly a 2 for you. 2, 0, minus 6, minus 8. And then I'll have 3, 6, minus 2, minus 4. Right? That's the first matrix I have associated. And now I can think about this row, these row operations that I'm doing is just everything that I do to these equations is just happening at the level of the coefficients, right? So now when I swap the rows, well, I got 2, 0, -6. Okay, this is -8. And then I got, notice this takes a little less space to write, 0, 1, 2, 3, and 3, 6, minus 2, minus 4. Right? And then what did it go to here? Well, it went to 1, 0, -3, -4, 0, 1, 2, 3, 3, 6, -2, -4. And then in this last one, I had 1, 0, -3, -4, 0, 1, 2, 3, and 0, 6, 7, 8. Okay? Right? If you have trouble reading any of these numbers, just know that they're the same as the numbers we had up above. Okay? So now I'm going to go back and keep working with the linear system. So I only have one thing with an x, which is good, and now I want to only have one thing with a y, so I'm going to add a multiple of this guy to this guy to make that happen. So what happens? I leave my x coefficient alone. And let me read it off of here so that I can actually see it. So I leave my x coefficient alone, and I have x the first equation alone, minus 3z equals negative 4. And then I have y plus 2z equals 3. And negative 5z equals negative 10, right? Yeah, so what did I do there? So to get to this system of equations, what I did is I multiplied this by negative 6 and added, right? So I zeroed that out. I get negative 12 added to 7 is the negative 5, and negative 18 added to 8 gives me negative 10. Okay? So I'm getting closer. I mean, this might seem kind of tedious, but remember that this is actually very fast for a computer to do. So then the next system of equations is what? Well, I can divide through by negative 5 to make this one easier to understand. So it's x minus 3z equals negative 4, y plus 2z equals 3, and now this just becomes z equals 2, and we've already found one of the variables. Now you might think at this point you want to do substitution, but it's actually better to just finish it off by using these elimination of variables. So now if I can add 3 times this equation to this equation, right? And that'll get rid of that negative 3z here. So I'll get x, and nothing earlier is affected, right? So that's good. So I multiply by 3 and add. I get x, blank, 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 equals, multiply by 3 and add. I get 6 plus negative 4 is 2. And now I'm only doing one thing at a time, so I'm being careful. So I still have y plus 2z equals 3, and I have z equals 2. And so I think I just need one more, and I'll have everything done, right? So x equals 2. Now I multiply by negative 2 and add to this. I get y plus no z, multiply by negative 2 and add. I guess I get negative 1, and then z equals 2. And so now I've got my solution, right? Everything's lined up on a triangle like that. So that implies that my solution is 2, negative 1, 2. Okay. Now next, let's remember that each of these things could have done everything at the matrix level. Let me just write down the corresponding matrices so that you can see what it looks like. Oh, this is a better pen. Right, so this would be what? 1, 0, negative 3, negative 4, 0, 1, 2, 3, 0, 0, negative 5, negative 10. This one I'm just dividing through this row, so these guys are unchanged. 0, 1, 2, 3. But this guy becomes 0, 0, 1. And I like it when I get 1 is equal to something because that corresponds to, in this case, z equals 2, right? Okay, so now I do this next row operation, and what happens? Well, so I'm using this 1 to zero out. These guys that I use to zero out other entries, sometimes we call them pivots. You'll see that coming up, right? So now what happened here? I get 1, 0, 0, 2, and then 0, 1, 2, 3. I didn't change that row yet. 0, 0, 1, 2, but that's coming. And then finally, the last one, I'm using this guy to zero out, so I get 1, 0, 0, 2, 0, 1, 0, negative 1, and 0, 0, 1, 2. Right? And so you can see the solution, 2, negative 1, 2, right, is just this, the vector here. If I think about this as being a column vector, this column vector actually represents the solution. Okay, so if I look and see what my next slide tells me to do, I bet, what have I forgotten to do here with all of this? Answer, did I check? Right? Did I check that 2, 1, negative 2 actually works in the original equation, right? So you might want to come back to this original equation and say, okay, what happens if I plug in 2, negative 1, 2? So is it true that whoops, this pen doesn't write. Is it true that if I have negative 1 plus 2 times 2, do I get 3? Yeah, that looks good. Check. If I have 2 for x, 2 times 2 is 4, minus 6 times 2 minus 12 is negative 8, so that's good. So it works in that one too. And now finally, 3 times 2 is 6, plus 6 times negative 1, so I have 6 minus 6, then I've got minus 2 times 2 is negative 4, so it works there too. So it's good that I checked. And then the last questions I want to ask about any linear system is the system consistent? Was there a solution? Yes, at least one solution. And is the solution unique? And in this case, we see that what we've done is show that there is exactly one unique solution. We'll see other examples where we don't have a unique solution, but that's all there is for this video lecture. Thank you for your attention.